Hello students, today we are going to study simple pendulum in detail. You know, while studying conical pendulum, we have taken the same system of simple pendulum. It is a point mass suspended by means of a string. Here, point mass suspended by a string from a rigid support, but here the string has some properties, like it is massless, it is inextensible, it should be twistless. So if point mass or heavy particle is suspended by means of massless, inextensible, twistless string from a rigid support, then this pendulum is called as ideal simple pendulum. But practically, massless string we cannot prepare, we cannot make it. Also, point mass heavy particle cannot be prepared. It should have some dimensions. Therefore, we take the system as heavy bob, heavy spherical bob, or simply spherical bob suspended by means of light inextensible twistless string and suspended from a rigid support. Then this system is called as practical simple pendulum. It can be heavy spherical bob suspended by means of light inextensible twistless or flexible string from a rigid support. Here is a rigid support. It is a practical simple pendulum. So for the study we use practical simple pendulum, but we have to make ideal simple pendulum. Now this pendulum, again there is one thing which is related to simple pendulum, that it should vibrate in a plane, in a vertical plane. So this point also we have to consider while the study of simple pendulum. Now in the point in this topic we have to show that the motion of simple pendulum is simple harmonic motion and it is linear simple harmonic motion. Actually, here if we show the motion of simple pendulum, then it is angular, its displacement is angular, or it traces the arc of circle, but we consider it as a straight path. So for that we have to impose some conditions. So here this system, it is denoted by point of suspension is denoted by O. Equilibrium position is denoted by this OA line. If the string is displaced through angle theta, as the system is oscillating system, this theta is the actually angular displacement, but it is also called as angular amplitude. So here the system is displaced like this. Then bob is at position AB. If it is released from this B, it comes to mean position and then goes to the position, which is left extreme position, say C. Here this is the C position and oscillates about the mean position A. Here this point is dark point we have shown. It is center of gravity of the bob. Center of gravity of bob. If we measure the distance of point of suspension from the center of gravity, this distance is L. It is called as length of simple pendulum. L is length of simple pendulum. And theta is angular displacement. Here the distance AB, this is arc of a circle, this is equal to x. This is x. It is actually arc of a circle, but it is taken as linear displacement because this theta is very small. Theta is very small. X is very smaller than L. This is the assumption. And second assumption is that the vibrations are in one plane and the plane is vertical plane. So once we have such arrangement, we can show the forces acting on the bob in this displaced position, means this right extreme position. So the first is that there is tension in the string. It is denoted by T dash. T dash is tension in the string. Here we denote it like this. T dash, tension in the string. Why we have denoted here T dash? Because in this chapter we have used T for period of oscillation. Therefore T dash we have used deliberately here for tension in the string. Now the next force acting on the bob is vertically downward. It is weight of the bob. It is vertically downward. Now this weight can be resolved into two components. One is along the string and other is perpendicular to the string. Perpendicular to the string. So along the string the component is mg cos theta and perpendicular to the string the component is mg sin theta. So here mg can be resolved into two components, mg cos theta along string and here mg sin theta is perpendicular to the string. Simple points which actually we have taken in the rotational dynamics for the resolution. Mg cos theta is balanced. Here T dash or tension is balanced by mg cos theta in figure, and here mg sin theta is directed towards the equilibrium position or mean position. Here it is A is mean position of the S.H.M. So mg sin theta restores the bob to its mean position. Therefore it acts as restoring force. Restoring force we denote here by F dash or simply F. So F can be equal to here mg sin theta by magnitude, but here we have to write it as negative because theta is say from OA to OB and restoring force is towards the mean position, As usual here, restoring force and theta have opposite direction. Therefore, we have introduced here negative sign. F is equal to minus mg sin theta. This is our first equation. From this equation, we have to further write some steps. Here we take sin theta is equal to theta radian, because this angular amplitude is very small that we have assumed. Our amplitude of S.H.M is also very small. Therefore, sin theta can be equal to theta. We can take here F is equal to minus mg into theta. It can be written again from the geometry of figure. Theta is equal to arc upon radius. Arc here, it is arc AB. Arc AB we have written already, it is equal to x, and radius of this arc or this angular path or this circular path is equal to L. This is L. Radius, it can be taken as OB. Here separately also we write arc is equal to AB, radius is OB, so we write x upon L. Theta is equal to x upon L. So in this equation number 2, if we substitute, then we write F is equal to minus mg into x upon L. Here, as m, g and L are constant, mass of bomb is constant, g is acceleration due to gravity at a given place is constant, L length we have adjusted is constant, then we can write F is directly proportional to x. And this is the condition for simple harmonic motion, linear simple harmonic motion, that is restoring force is directly proportional to the displacement from the mean position and it is directed towards the mean position because there is negative sign in this equation. Negative sign indicates the directions of x and f are opposite. So here this condition proves that the motion of simple pendulum is linear simple harmonic motion. So now from this expression we turn to the next point, which is period of simple pendulum. So before going to that, again we take one modification in this equation, that consider equation F is equal to minus mg into x upon L. If we write F upon m, means adjust the relation like this, F upon m is equal to minus gx upon L. F upon m is a, means acceleration of the bomb is minus gx upon L. This is equation number 4. Here also we write a is directly proportional to x, which is the condition of linear S.H.M. Acceleration is directly proportional to displacement and directed opposite to the direction displacement. So from this relation, again we write a upon x is equal to minus g upon L. If we take the magnitude, it is equal to g upon L. G we write here for the distinguishing it from 9. A upon x is equal to g upon L. This is the equation number 5. Now from this equation we derive the deduce the equation of period of simple pendulum. How can we derive it? We know the expression for period. Period is of oscillation. you know it is defined as the time required for one complete oscillation, and it is related to the angular velocity or angular frequency by this relation, twice pi upon omega. T can be equal to twice pi divided by this angular frequency we have derived as acceleration per unit displacement. This is the expression we have derived at the beginning of the chapter, or second point in the chapter. It is twice pi divided by acceleration per unit displacement. From this equation 5, it is A upon S, means acceleration per unit displacement, it is equal to G upon L. So inside the under root it is written as G upon L, and the final expression for period we write is T is equal to twice pi under root L upon G. This is the expression for period. We give the number as 6. So this is the simple derivation for the period of simple pendulum. So in the first part of the study of simple pendulum, we have shown that its motion is linear simple harmonic motion, because force is directly proportional to x, acceleration is directly proportional to x. For that we have assumed that the motion of pendulum is in vertical plane, only one vertical plane. Angular amplitude is small. So I can write here the assumption. So the motion is in vertical plane. Theta is small, means amplitude is also small, and here the third assumption we have not explained in the explanation, but that assumption is also there, that air resistance or air drag is small, or it is neglected, it is not considered. Air resistance is not considered in this case. Actually, air resistance is there when we perform the experiment or when we study the oscillations of simple pendulum. But in this discussion, we have not considered air resistance. So by assuming these points, we have shown F is directly proportional to x because theta is small, A is directly proportional to x. From this we have obtained the relation for acceleration per unit displacement, and then finally we have the expression for period. T is equal to twice pi under root L upon G. Now we write that expression here. T is equal to twice pi under root L upon G. This is equation number 6. Now from this equation also we conclude some points. The first point is that T is directly proportional to square root of length of pendulum when G is constant. So at a given place, G means acceleration due to gravity is constant. We can say that period of simple pendulum is directly proportional to square root of length of pendulum. Second conclusion is that T is inversely proportional to square root of G. Means period of simple pendulum is inversely proportional to square root of acceleration due to gravity. From this relation we can write. In this relation, mass means M is absent. So we can say that T is independent of mass of ball. So this is the third conclusion. And fourth one is that T is independent of amplitude of simple pendulum, or simply amplitude. So here these are four conclusions which we have drawn from the expression of period of simple pendulum. These conclusions are called laws of simple pendulum. So here specially laws are not there, but conclusions can be taken as laws of simple pendulum. So this is about one simple point in this point is laws of simple pendulum. Now the next point in this is that seconds pendulum. Seconds pendulum, the name itself explains the idea, which is for the simple pendulum, if the period is equal to 2 seconds, then that pendulum is called as seconds pendulum. We have to derive the expression for its length from the equation 6. So consider T is equal to twice pi under root L upon G. If we substitute T is equal to 2, we get 2 is equal to twice pi under root L upon G. Here we can write 1 is equal to pi into L upon G. Squaring on both sides we get 1 is equal to pi square L upon G, and finally we get L is equal to G upon pi square. So this is equation number 7. L, length of seconds pendulum, suppose we denote it by Ls. Ls is equal to G upon pi square. It is the length of seconds pendulum, where the acceleration due to gravity is G. So from this relation we can calculate the value of acceleration due to gravity. So this is last point in the study of simple pendulum. So today we stop here. Thank you.